welcome to Foresight Biotech and Health Extension Strategy Group, sponsored by 100 Plus Capital. It's really lovely to see all of you here. Without further ado, I want to give the mic up to Michael Snyder from Stanford University, and he will be talking about monitoring personal health and ageotypes using big data. I'm going to share more info on Michael here in the chat, and that will be in the future also available under the YouTube video. There's a lot of different, if you're watching this on YouTube, there will be a lot of different updates shared on how to join this group. So if you're watching this as a video, it works out if you just check out the YouTube description underneath. Okay, Michael, thank you so much for joining. I'll be in the chat in case anyone has questions. And that's also where people can find your bio who are here in the Zoom meeting. All right, thank you very much for joining. You had a ton of excitement for the talk just in the emails that I sent out about it. So we're really excited, and yeah, the stage is yours.
Okay, great. Well, thanks very much for having me here. I did decide to talk about my favorite topic, which is trying to use big data to improve people's health span. And of course, I'll talk about Ageotypes, and I can't resist saying some of our latest work about COVID-19 because I'd love to have you all sign up for some studies we have going on here. So I will say that a lot of this is, I guess I have presented in the last few years. So if you heard me talk in recent years, you may know a lot of what I'm going to say. You can drop off if you like. I do have lots of conflicts. I'm involved in a number of companies and some others I see that aren't listed here. And yeah, so you can trust whatever you like. So I think medicine, many of you may agree, is broken in many different ways. And this is just one of those ways. It's very focused on treating people when they're ill and very reactive. When people are healthy, we measure very few things. And generally when people are healthy, it's very infrequent we measure them. And the biggest problem, I would argue, is that nearly every decision about your health is based on population-based measurements. And I think certainly this crowd would agree that we should be focused on keeping people healthy, as such be very proactive. And certainly with new technologies, we can measure many more things. The frequency, I would argue, should depend on what you're at risk for and what your personal trajectories look like. And again, I think we'd all agree we should be doing individual-based medicine rather than population-based measurements, which physicians will tell you we do that now, but I don't think it's nearly at the level at which it should. By the way, I don't mind being asked questions as we go along. I'll try and, it's hard to see the chat. So if you want to just, blurt in, that's fine by me. So anyway, we should really be focused on precision health rather than precision medicine. And here's an example I'd like to show. There's actually quite a few examples now out there of this sort of thing where we all have certain misconceptions, and one that we're raised with here is that your oral temperature is 98.6 when you put a thermometer in your mouth. And the reality is that the median value is more like this, 97.5. There's a number of studies that support this. I myself have 97.3. It's dropping a little bit over the last 10 years. But the more important concept here is that there's a spread. So this is a 25th quartile, and this is a 75th quartile. And so what that means in today's world is that if you have a normal baseline of 94.6, you go to physician's office and they measure at 98.6, that you're told you're healthy, everything's fine, what are you doing here, go home. When the reality is you're at 4 degrees Fahrenheit, you're really probably not well because you're way over your baseline. And so that's a theme that we'll hammer many times. You should really know your baseline so that you can see deviations from that. We think that's powerful in general for trying to detect illness. And so your health is influenced by many things, which we can quantify now. We can sequence people's genomes pretty well. Some of these areas are a little clunky. We're spending a lot of time on this, actually, environmental exposures and pathogen exposures. But you can now start to measure these: stress, food, exercise. This one's pretty good with activity monitors and things. But we can quantify these at some reasonable level, but more importantly, we can quantify their effects by actually doing deep molecular profiling on people to be able to actually see the effects of these things on people's molecular and physiological profiles, which we think is powerful for monitoring their health. And so just to show you what we've been up to for now the last, I guess, 11 and a half years, we set up something we call personal omics profiling, where the idea is to collect big data on people using advanced technologies. So we'll sequence their genome, and then we take lots of other molecular measurements. For example, we'll follow people's DNA methylome, which is their epigenetic signature, if you will, along with these other measurements. Many of these are done out of your immune cells, your peripheral blood monocyte cells, but some are done out of your plasma, which is, you know, your blood that without the cells, that is great markers for disease states. So we'll follow proteins, these immune markers called cytokines, metabolites, lipids. We actually are doing a lot here and even solving diseases by these profiles now. And we also take deep measurements on people's microbiome, so their gut, nasal, and more recently, tongue and skin. And at the same time, we're doing deep clinical testing, questionnaires, some advanced tests like stress echoes and glucose measurements you'll hear about later. And then about 8 years ago, we brought in the wearables. I'll talk about that as well. And so one aspect of this is deep data, and the other aspect is longitudinal, which we think is equally, if not more important, getting people's measurements over time while they're healthy. So we sample people roughly every 3 months while they're healthy, and then take 5 to 7 additional samplings during periods of illness like viral infection, things like that have turned out to be powerful. And I see this is out of date, but we've been running this study now for about 8.5 years on most people, some a little longer, some a little less. And it's a smallish cohort, 109 people, but the goal is to be able to see what we can learn from the so-called pilot study, and then talk about how we're trying to scale this. So you might say, well, why are we doing all this? Well, the goal is really to be able to try and understand what it means to be healthy. We're profiling people while they're healthy, and then try to see how that changes over time, which is very relevant to aging, which I'll get to in a minute. And then, what happens during times of illness, like a viral infection. And perhaps most importantly, if we bring these advanced technologies to bear on, normal people, can we actually learn things that are useful for healthcare that will basically be valuable information? And with regards to the latter, what we've discovered is just in the first 3.5 years, is now going on longer, but basically we had 49 major health discoveries, 67 if you count hypertension, and it covers a wide range of areas, cardiovascular disease, hem-oncology, metabolic disease, infectious, so on and so forth. And some of these we would argue is a pretty big deal, like we caught someone with early lymphoma, 2 people with these pre-cancers, MGUS, smoldering myeloma, 2 people with serious heart issues, 1 picked up from genomics, talk about that in a minute, other through wearables, some people with diabetes, so on and so forth. So, and it was no one technology that did this. It was sometimes genomics, sometimes, the blood markers that we're doing, proteomics and metabolomics, and sometimes it was the wearables. And so together they were extremely powerful. Sometimes it was a combination that was also very, very powerful. So, and so again, this turned out to be, we think, quite useful. And just to go into this in a little more detail, basically the genome sequencing was important. 13 people, 12 learned something just straight up from what's called Mendelian diseases, and 1 person from their pharmacogenomics. They were on the wrong drug, it turns out. But anyway, from these 12 people who had what's called a Mendelian, they learned something very, very important. Like there's 1 individual with a BRCA mutation, indicating that they would be at very high risk for breast cancer. And then there were other cases as well. One fairly young person had a mutation in this gene, which puts them at high risk for cardiomyopathy. And it turns out they have a heart defect. They did a stress echo follow-up, and so they're on drugs now as a consequence of this medication. Another, also fairly young person, had a mutation here at risk for certain kinds of tumors. And it turns out that they did a whole body MRI follow-up, and once you know they had early thyroid cancer, and that was removed. They were to keep their thyroid, so they didn't need replacement therapy and so on. And here's an individual, 9 individuals were thought to be type 2 diabetic. One of them turns out to be not really type 2, it's called a MODY. It's a different kind of diabetes. And the way you treat a MODY person is typically very different from a regular type 2. And so they were on suboptimal medication for quite a few years. So bottom line was genome sequencing was powerful in a number of cases. Imaging turned out to be powerful in at least one case where we caught a person with early lymphoma. They had a large spleen, but they also had elevated blood markers, and the combination was quite powerful. And then here's an individual with elevated, there's 1,000 samples here, and this person's 2 samples were just way different from everyone else's for this particular marker. It's called IgM. And turns out with follow-up, it's pretty clear they had this, what's called a precancer, that puts them at high risk for getting full-blown cancer. So they'll get monitored a lot more frequently. I have my own ideas about what they should do in terms of stem cells. But I should warn you, I'm not an MD, so everything I say you can take with a grain of salt. Just check the chat here. Okay, looks like we're good. All right. Here's people with plaques in their arteries. 6 individuals had that. I'm one of the 6. Generally small, but the recommendation is to increase your statins, which is done for me. My plaque needs to be shrinking. We're very interested in type 2 diabetes because I myself am type 2 diabetic, actually predicted from my genome. And as I mentioned, 9 individuals were thought to be type 2 diabetic coming into the study. Well, it turns out 2 individuals were type 2 diabetic who didn't know it. And a lot of folks were pre-diabetic and didn't know it. And that's very common. 9 out of 10 pre-diabetics don't know they're pre-diabetic. I'm pretty sure a lot of you listening to this talk right now are pre-diabetic and have no idea. And we think that's a big deal because 70% of pre-diabetics will go on to become full-blown type 2 diabetics. And so catching it early to be able to better manage is quite useful. Now, very, very interested in how do you become type 2 diabetic? Do you just gradually get there? Does something trigger it? And this is very relevant to the current COVID pandemic, as I'll get to in a minute. And so we followed from these first 4 years or so, how did people become diabetic? And 9 more individuals became officially diagnosed as diabetic, and others had diabetic range measurements. And others became pre-diabetic. And it turns out of the 9, 2 people got there through weight gain, which is kind of a typical way you might become type 2 diabetic, but the other 7 didn't gain weight. And so 5 of the 7 just gradually became diabetic. It's not clear why that would happen over time, but they did. And age is certainly the #1 risk factor for type 2 diabetes. And they either got there through fasting glucose measurements, hemoglobin A1C, which is a measure of elevated glucose, or something called an oral glucose tolerance test. People were first diagnosed by these different means, which have slightly different measurements. So we're actually working on this now. We think we can subtype diabetes much, much better than is being currently done. I won't get into that here. But anyway, 2 other people spiked their way into diabetes. And I'm one of the 2. This is me, about 8 years of data. I first became type 2 diabetic after a nasty viral infection. And so we think I'm genetically predisposed, and then the viral infection triggered it. I know that looks like a tiny blip, but it's about 10 to 12 months. And I actually did a whole lifestyle change of cutting out all sugars and started running and doubled my biking and got it under control. And then later it actually came back when I stopped running. Ironically, I stopped looking at my sugars because it's so boringly low. And then somebody else looked at it here and said, Mike, you're back to diabetic again. And then I said, oh, yeah, we went back and looked. And sure enough, I'd stopped running here. I also had another viral infection. So we think it's still not, again, running clearly helps, but the viral infection may also trigger it. And then I did start running. I could never get it down to normal levels, and gradually it kept creeping up. And so I basically switched from running to weightlifting. You can't tell, but I've been lifting weights and gained 10 pounds of muscle mass, and that still failed. My glucose kept going up, and there was a logical reason for trying to do that. Finally, I went on metformin, and that failed too. So I went all the way up to 7.5. And then actually the way we got it all figured out was I basically got more data, and it turns out I make insulin just fine and my cells respond to insulin. So you might say, well, what's wrong with you? Well, I actually am very slow in my glucose disposition. I don't release insulin from the pancreas, it turns out. And there's a drug for that, it's called rapinolide, and I'm actually a pretty good responder to that, whereas I wasn't to metformin. And so we call this precision diabetes. By knowing better what's wrong with you, you can prescribe the right drug for the right situation. And so this could actually be done on everyone fairly inexpensively, and it's not. and that's, I would argue, a flaw with our system. One of the biggest things we learned, this will relate to the aging, is that people all have personal profiles and we're all very, very different. And it doesn't matter what kind of measurement we make, whether it's your cytokines or your clinical tests or your metabolites or even your RNA or proteins in your blood. We're all different. And so each dot here is a different visit. And for simplicity, I'm only showing 12 people with 10 or more healthy visits, but each dot is a different visit and each color is a different person. I'm the light blue, and all my dots tend to, cluster together, the red person's together, yellow, brown, so on. So we all have these personal profiles and they're quite stable. In my case, there's 6 years of data here. My dots are all together. So we think these profiles are fairly robust. They're pretty, if you will, hardwired in the sense that I think people have pretty standardized habits, and that's probably what's contributing this as well. But even beyond that, if you do get hit with a viral infection or some other perturbation, we've run people through all kinds of perturbations. And by the way, we're running more studies now. Feel free to sign up. Some of them you have to be in the Bay Area for, but some you can be anywhere in the world. Anyway, if you do a perturbation experiment, in this case, people ran to their VO2 max. So really intense exercise for a short burst, like 10 minutes. And you will shift your profile, about half your molecules change, but you will still look more like you than anyone else. So that's what these different colors are different people, and we sample them different times after exercise. And so again, people have these very, very robust profiles that don't shift. And so the reason this is a big deal is that the difference between the healthy you and the disease you is actually often less, probably usually less, than the difference between people. And so if you're trying to see when you first get ill, you won't pick that up very easily if I take a sick measurement on me and compare it to 500 healthy people, because the difference between people is very, very large. But it's very, very easy to see a sick Mike Snyder from a healthy one if I have a healthy profile. So we're big believers you should get your healthy profiles and use that now. So, and that's an important basis for a lot of what I'm about to tell you now. So I'm going to see if there's any questions in the chat. Oh yeah, so here we go. There's some citizen scientist questions. Well, there's a long question from Carl. I don't know if I can read that quickly. All right. Let's see. Well, let's see what we can do.
Mine's a good one to leave to the end.
Okay, great. Well,
I love this work, and I just, it's all about scaling it and making it bigger and stuff.
Cool.
So that's a good end comment discussion.
All right, bring it up at the end. I tried to save 10, 15 minutes at the end. All right. Have you done measurement of baseline heat shock response? Not sure. I haven't done a heat shock. We have done some, like I've gone into one of these bariatric things, these freezing things, and I haven't yet got the data back on that. That'll be interesting. And others are doing hyperbaric, measurements that I think will be fun too. We don't have data back on that. That'll be pretty cool. Is there a commercial service? I'll touch on that one. Totally conflicted there. And we're going to get to Carl's at the end. All right, great. So, all right, well, I don't mind answering questions as we go along. So if there's one urgent. So this is just the basis of what we're doing for finding disease, but then there's a lot of fun stuff you can do. And some of this, I think this crowd would be very interested in. So we've just reflected on the data. By the way, the data is entirely out there. Nearly everyone's agreed to make their data, including their genome sequences, public. So you're welcome to take a look at this. All right. And anyway, one question that kind of appeared is that we've been taught since we were little that there's 4 seasons and they're all 3 months each. And if you just reflect on that, you might say, well, who says, who says there are 4 seasons? Maybe there's 15, maybe there's 3, who knows? And why would they be 3 months each? That doesn't even make any sense. So we said, well, let's take a look at the patterns in the data and see how many biological seasons there really are. So what we can do is, I told you most molecules don't change, but there's about 1,150 that show a seasonal pattern. And here's some examples here. Here's that hemoglobin A1C, see when it peaks, red blood cells, and so on. And so some of these were known already. Most are brand new. People hadn't described them before. Even your microbes, you can see which ones are seasonal. It just so happens we had nice patterns throughout the year. And so we can then say, well, all right, we have these different patterns, these molecular and microbial patterns, how many basic patterns who they fall into? And the answer is two. You show that mathematically, that there's two major patterns. There's some molecules that don't quite fit in here, but the most of them do fall in these two patterns. And then you say, well, these are people, by the way, in Northern California, 3 are from Southern California. So you might say, well, of course, they're from California. Of course, there's 2 seasons. One should be winter and one should be summer. And you would be half right. So this is the winter pattern. These are the molecules that go up in winter. And it turns out they're acne, acute, phase thing. That means things that come up from viral infections. So that makes a lot of sense. The other pattern turns out to be late spring, April, May. And in hindsight, it makes a lot of sense. That's when allergies are pretty rampant. And so asthma and allergies go up at this time. But there's other molecules that are changing and peaking at that time too. Things involved in cardiovascular disease, metabolic health, type 2 diabetes are all peaking around then. Some things I don't fully understand, seizures and sleep. And we think some of these metabolic and cardio markers are going up because even in California, people are less active in winter. It rains, and for us, it gets cold here. It can get down into the 40s at night and that kind of thing. So people, we think, are more dormant, even in California, and that probably leads to this sort of pattern. And I think this is relevant for a lot of reasons. One is there's clinical markers associated with this, as well as microbial markers. Can't remember if that's, I guess took out the microbes. So there's some very interesting markers. And we think this is relevant because you can take this into account when you're starting to see your molecules change. For those of you who are quantified self folks, you will probably experience these kinds of perturbations. And some of it might be useful to know, because if numbers are getting too far off, you might want to, make a little extra effort for exercise in the winter if you see yourself dipping a little too far out of range. So anyway, we think that's important. So here's the part that's most relevant to aging and for this crowd, which is because we're following people over time and profiling them while they're healthy, we can say, well, how are people changing over time? And we did the standard sort of thing, looking for markers in old people and young people. And we see, hemoglobin A1C, other things that are higher in old folks versus young folks, and get a lot of the same, but we get a lot of new markers because we're profiling so deeply. But the more interesting thing to do is just follow people personally to see how they're aging. And we had 43 people with enough data. We don't think it takes very much. 5 measurements, we think, within 2 years gives a pretty good profile on how people are aging. And it turns out everybody's aging differently. And I think this isn't a surprise, but it hadn't really been shown. So this is me on person 1. I give a lot of measurements, given several hundred since the study started. And I'm a typical ager. Coagulation, metabolic markers, they all go up with time. Here's a person where their top pathway that goes up is cardiohypertrophic signaling pathway. And it turns out, so they're a cardio ager, if you will. And in hindsight, we look back at this and they have stage 2 hypertension, which sort of fits with this concept. So we think this person's a cardio ager. And as I say, we had 43 people. So just like the seasonal data, we could say, well, how many patterns does that fall into for these 43 people? And the answer is there's 4 major patterns. Now, I know there are more than 4 patterns out there. It's just that that's all we're statistically powered for. And we call these Ageotypes. These are aging patterns, if you will: kidney, liver, metabolic, and immune. And so each column's a different person. Each row is the Ageotype, if you will, the markers that are shifting. And the folks down here are aging in all 4 categories, probably typical ager. This person's 3 of 4. I'm in here somewhere. I'm not much of an immune ager, I'm happy to say. Hope the exercise is helping for that. And this person's kidney agers, kidney and metabolic, and so on. And so what we think is that people are aging just like cars. The whole car gets older. And the whole person gets older, but some parts are starting to wear out faster than others. So like this kidney ager and so on. And so we think this is actionable information for a couple of reasons. One is there are clinical markers associated with these Ageotypes. So for example, hemoglobin A1C is one of the markers in the metabolic age. It's not the only one, by the way. And creatinine's another, and so on. So there is aging markers that are known clinical markers, although the Ageotype we think is a little bit better description of what's going on. And so to dig into this a little bit deeper, The last column with the star, sorry, probably should get this displayed better. This is what the group as a whole is doing. So the group as a whole is going up in hemoglobin A1C. But if you look at the individuals, you can see 4 people are going up. The dark bar means statistically significant. And 4 others, though, are actually going down. They're reversing their hemoglobin A1C. And there's good reasons for this. This is an easy one to explain because 2 of them went on diets, one started exercising, one went on, lost weight. And so they were reversing their hemoglobin A1C, and that is a good fashion. Their Ageotype was actually shifting. Now, here's another one that we don't have as well explained, creatinine, which is a mark of kidney function. And you see the whole group's going up, which we would expect, but 10 people are actually going down, and 8 of the 10 are on statins. It's a statistically enriched proportion. So something about the statins was improving this. And I don't think it's just a loss of muscle mass because they seem to be pretty constant for that, as far as we can tell. It could be subtle when we miss it. But anyway, there's something about statins that might be helping here. And so that's one I don't have a full explanation for. So why is this a big deal? Well, something got lost, which is why you can't read this. So, and the reason we think this is all a big deal is that, there's a ton of stuff out there to try and get people to improve their health span. And, I do my thing like the rest of us. I go to CVS and I see this giant shelf of all these supplements, and, they're laid out there, and I eat my share. But of course, how do you know that they're any good? How do you know they're working? And, of course, you can buy products that are promoting themselves as anti-agers. And we don't have good markers for that. Certainly the DNA methylation markers is one of the best ones that's probably out there, but it's still a little bit slow, I would argue, compared to what we could do with these Ageotype patterns. So I think in principle, we could actually try to do this better. And therefore know if these things are working. And that's why I think these markers are important, and self-tracking is so important. And finally, I'll just say that, we can also, look at our cohort and see how people are aging using what other markers people have done. And this is Morgan Levine's PhenoAge. Some of you may be familiar with this, with 9 markers. And so we can look at people's phenotypic age compared to their chronological age. And sure enough, we find people that, are above the line, meaning they're older than their chronological age, and their slope, to be honest, isn't so good. And then there are people that are below the line that seem to be younger than their chronological age. And I don't think they're really reversing their age, but because the statistics isn't quite so strong. I don't have error bars on all these lines or get too messy. But nonetheless, their slope is at least in a good direction compared to the folks above, many of the folks above the line. So the point is that we can actually follow people's aging patterns. And I think there is actionable information here that you could, again, act upon to be able to try to improve your aging. Now, one person asked, I saw in the chat, how are you going to scale this? And as an academic project, this was a really deep, expensive project. And so we spun off a company, it's called QBio, totally conflicted. But what they're doing is a medical version of this, along with whole body MRI. And just from the first, this is just over 100. They have many more than that now. But right away, they found things that were pretty important. And here's a list here, like, certain cancers, like early stage pancreatic cancer, which, just never gets discovered early. And some of these other things, they're either picked up by what we call multivariate evidence. So we might see several lines of evidence. And this is a big deal because you'll see in people's patterns, people will be in a normal range, maybe at the low end. Suddenly they'll jump up and they'll still be in the normal range, but they'll be at the high end of normal. And, that gets ignored in today's medical world, but we would flag that and say, well, you've jumped up and something's up, and you look at other markers, you can see something might be going on. And so again, that relates to this other part, which is the longitudinal part. Really, by following people's changes, you can really learn a lot. And this is almost entirely ignored in today's medical world. So we think this is super powerful for trying to be able to better manage people's health. And it's not cheap. It's $3,500. It's, you can argue that's expensive or cheap. It's cheap if you think about what it costs if somebody gets a heart attack or has some serious issues. It's expensive for the average person. So, but anyway, I think over time we'll get this even cheaper and better. So we think this is the way to scale it, and I hope to get it out, to everyone, to be honest. Now we're very keen on wearables. Let's see how we're doing time-wise. So I wanted to tell you about some of this because this is inexpensive and something you can all do today, basically. So we're very keen on these. We got involved in this when Fitbit first came out, and they were using them, as you know, for fitness trackers and heart monitors, really for activity. And people would wear them for 3 months and then get their patterns and throw them in a drawer. And we realized that these are pretty darn powerful for following people's physiology because they'll literally take hundreds of thousands of measurements on you every day. Some devices, you may know, take 2.5 million measurements per day on you. And they're measuring all kinds of different things. Depends on the devices. They all measure heart rate variability. Some measure respiration rate, many temperature. Some measure blood oxygen, which by itself isn't usually so accurate, but the delta can be pretty accurate. And some will measure blood pressure and so on. So you can measure all kinds of cool stuff with these. And also already there are lots and lots of people wearing these devices. 50 million people in the US have a smartwatch. And so we started putting these on people, and sure enough, everybody's different in their measurements, heart rate, and so on and so forth. And then we started looking for, what can you learn from this by seeing shifts in people's physiology? And fairly quickly, we learned that you could detect infectious disease. And in fact, I picked up my Lyme disease of all things with a smartwatch and a pulse ox. So basically what happened was I'd been at my brother's place in rural Massachusetts, where 55% of ticks are Lyme infested, for one day, helping them put up fences. And then 2 weeks later, I was flying to Norway and discovered this drop in blood oxygen and elevation in resting heart rate. And it happened on the plane, but then it was still there when I landed. So it's very clear it was a persistent effect. And I later got diagnosed with Lyme. I kind of warned it was Lyme. Anyway, when I landed, but anyway, went back and looked at all data, and we had 4 times when I was clearly ill, as measured by C-reactive protein, it's called. So 1 was a Lyme time, 2 were viral infections here, we now know here. And the 4th time was I was asymptomatic, but had elevated. My CRP was just as high as the other times, indicating I was ill. I just didn't know it. And sure enough, every single time I was ill, I had high resting heart rate, best plotted by outlying measurements, can get it from median values, as well as skin temperature. So we went on to write an algorithm that worked well for heart rate, doesn't work well for skin temperature, but where you could build people's baselines and then look for the shift from baseline. It's kind of called a delta plot, if you will. And we'll look for these shifts. And this is when people's heart rate, this is me, went up. And in every case, we could pick up the shift in advance of symptoms. And it worked well on me. It worked well on 3 other people, one of whom got sick twice. So every single time, we could see this jump up in heart rate before symptoms. So as you might imagine, we were improving these algorithms, trying to build a scalable system. And then along came COVID. And here's where we are as of yesterday. We're in these waves that are pretty darn big. And this one is actually heading up, the one we're in now, obviously mostly amongst the unvaccinated. So anyway, it is what it is, 150,000 people per day getting ill from COVID. And so we asked whether we could detect COVID from a smartwatch. And by the way, the way it's measured now is the gold standard is PCR, which is too slow. It takes a day. And of course, you don't do it every day because it's not that cheap or convenient. And then the more convenient ones use a thermometer, but certainly these infrared ones that they shine on you, I don't know about you, but when it's wintertime, I measure about 33. So I'd probably be dead if this were accurate. And they always let me in anyway, even though they measure you at 33. So I don't know how effective this one really is. And of course, a lot of people don't get a fever anyway. So it's not so clear this is the best thing for COVID. If you think about it, it's a 300-year-old concept that we're implementing on a 21st century problem. So anyway, we wanted to see if wearables could actually be powerful here, and so we launched a study. We had one running already, but the new study, has 53. Right away, we got 5,300 participants, 32 what we call gold data sets, where people were COVID positive and they were wearing their smartwatch. In this case, Fitbit, we started with initially, and they also had a a diagnosis date and a symptom date that they recorded and verified. And so this is our very first participant. This is pretty cool. Basically, this is a diagnosis date here. This is a resting heart rate shift from their baseline. And this is diagnosis date. This is symptom date. And you can see their heart rate jumped up 9.5 days prior to symptom. It's a signal you can't miss. And I'll talk about our alarming method in a minute that can capture this. And so that worked well. It turns out we could detect 26 of the 32, 80% of people it worked for. So it's not 100%. So it's hard to get a baseline on certain people, stable baseline. And so those are tough ones. But for most people, it does work. And it turns out it works a median of 4 days prior to symptom onset, 7 days before diagnosis. So we could pick up, again, a signal for some cases quite early. And it's not specific for COVID. Other illnesses will show this as well. The median's 2 days before other illness. These are non-COVID cases. And that makes sense because COVID has a longer pre-symptomatic period than most other illnesses. And it does pick up other stressors as well, meaning psychological stress. We'll see a signal because your heart rate usually goes up. And too much alcohol, not just 2 drinks for dinner, but if you really tie one on, you're hungover the next day, you'll probably set off an alarm, as we'll show you in a minute. And so we built an online detection system that lets us follow as we take your baseline and then look for the shift in terms of, with several kinds of algorithms we're using. We're using 3 different ones now. One is around resting heart rate. One is around heart rate plus steps plus other sleep measurements, and others are different combinations of things. And so again, it does work pretty well. You can see this, we can see these alarms. This is retrospective data going off well in advance of symptoms, again, as a red, and diagnosis of purple. There are other alarms that go off. We've tuned it so it goes off roughly every 6 weeks to 2 months. And people do get bumps around the holiday, both in the earlier holiday as well, this like holiday of 2020 as well as holiday of 2021. Well, sorry, last winter, previous winter. It's very common to get a holiday bump. I don't know if it's alcohol or getting ill or stress from in-laws at all is triggering. It's not clear. But we are recording this now. It's kind of cool. Actually, it turns out fatigue or people lack of sleep seems maybe one of the strongest correlations. Here's other illnesses that do trigger this, and even healthy people will get these bumps. These are real signals. We don't always know what's triggering them. They could be asymptomatic effects, not so clear, but I'll come back in a minute. All right. So last November, end of November, beginning of December, we launched our real-time alerting system. So we built now yet another algorithm that actually, it's pretty sensitive for night, and it's built in a way that lets us scale. So we have this cloud-based system that in principle can literally follow millions of people, pull in their smartwatch data, follow them in real time, and ping them when we get an alert. You do it to sync it up. I want to set it up in a way you don't have to sync it, working on that. But right now, every day you have to just check, and if you have a positive signal, it'll show up. And so it does work. It's following these people in real time. We have several thousand people signed up already, about 4,000 or so. And I'm hoping all of you sign up, by the way. And this is just one of the early examples where, again, we'll send this red alert, if you will. In this case, the red alert went off 3 days prior to symptom. They were diagnosed the next day. And I can update this now. Out of 80, I think it's 84 cases, we have 80% detection rate. So it's even slightly better than this. So 80% of the time, we send this alert either at or before the time of symptoms. So we think that's pretty good. Love to do better, of course. And the other thing that's pretty nice about it is that we can pick up asymptomatic cases. So these people are getting randomly tested, had a positive signal, and then we look and see what's going on. And sure enough, like there's a case where it's very clear they had a positive signal coming before this diagnosis date. There's another case here. We have 14 cases, 10 cases, we pick up a nice strong positive signal at or before infection. I forgot to say the new alerting system works for a Fitbit and Apple Watch. I'm sure it'll work for Garmin too. We just don't have as many people enrolled for that. So I don't think this is the only kind of data we want to gather from smartwatch that is infectious disease data. I think we can get other kinds of information. So we built some machine learning models to be able to try to make predictions of people's clinical measurements. So here's hemoglobin, red blood cells, hematocrit. You can get some predictive value, not clinical grade predictions, but enough to tell you that something might be up, and that could be useful for dehydration or anemia. Here's some glucose level measurements, hemoglobin A1C, glucose, and so on and so forth. So we think, and this is all done with a very old smartwatch. I think if we could do this with the new one, the newer one, we'd even be better. See how we're doing time-wise. Yeah, I'll just say a few words about glucose monitoring, then wrap up to save time for questions. But basically, we're very interested, again, because of my situation and just the new technology of being able to measure people's glucose. And there are these continuous glucose monitors that you put on yourself that will measure your glucose levels. So we started putting these on normal and pre-diabetic, even a couple of diabetic folks. And what we discovered is that, some people have good glucose control, some are moderate spikers, and some are pretty severe spikers. And we could take these data, I won't get into details, but we can actually start classifying what these patterns look like and classify people into what we call glucotypes, where people are either low spikers, medium spikers, or, super spikers. That's not a good thing, by the way. And so we started, testing people on different foods, and we had found, as did Aaron Siegel, that different people will spike to different foods. So some people will spike to bread, others to pasta, some to berries, and so on and so forth. And it varies. Now, nearly everyone spikes to white rice, and nearly everyone spikes to cornflakes and milk. And I'm pretty sure this is not good for you. This maybe is worse than smoking. I'm not quite as sure about that. But anyway, the point is it's definitely can't be good for you. So that's probably the only thing you'll remember from this talk. Don't eat cornflakes and milk. Anyway, this is we can see different people spiking different things. And Aaron Siegel has shown that at least part of this can be explained by the microbiome. I think there's other factors as well. I forgot to say, but in my case, my methylome shifted after I first became diabetic, and the second time too. So we think there may be epigenetic effects going on here. It's actually my metabolic genes that seem to be most affected by these shifts in methylation patterns. Kind of cool. Anyway, so we, as I say, started looking at people and classifying them. And sure enough, there are some people running around that's complicated, but there's some people running around who are severe spikers, who are healthy by all standard measurements, by fasting glucose, hemoglobin A1C, even oral glucose tolerance tests. And that surprised me, and they're spiking just as badly as diabetics. And so we think these measure slightly different things, and that's probably why they're picked up. It relates to the subtyping I mentioned previously. So I think these devices are very, very powerful. Again, 100% conflicted, but we started putting these. So again, this is, people always ask me how to scale, and I think the way to scale is always form companies, because I think academics aren't so good at scaling. They think they are, but they're not. And so I think companies are a great way to scale how to do this. So we formed a company, January AI, that's using CGM and has built a beautiful database with GIGL that can actually really follow people's glycemic index, makes food recommenders, that sort of stuff. And one simple study we did that we just published recently, so we could show just wearing a CGM and using a simple app that January AI has, will actually improve people's, they call it time in range, the amount of spiking that they have. So what we discovered, first of all, is that, again, healthy people, there's a lot of healthy people who are actually are spiking, like pre-diabetics, where even fewer type 2 diabetic. We discovered very similar to the previous study. But here's what I wanted to show you, which is that, people who wear a CGM, even for just 10 days, believe it or not, can actually improve their spiking, if you will, called time in range. And so here's an individual who was, the first 2 days, and here's her last 2 days. They've with just by wearing this and looking at these things, they're very powerful. If you ever worn one of these, they're very eye-opening. You'll see what spikes you, and it's often surprising. It usually makes sense in hindsight, but it's surprising when you're wearing them. And so it turns out, over 90% of healthy people actually improve their time in range, and even 60% of type 2 diabetics improve their time in range. And so we've actually rolled this out, and there's a whole program around this. So shameless promotion here. But anyway, if this interests you, that's something you can pursue. So academically, what we've been doing is we built what we call a personal health dashboard, where we bring in people's wearable and other data onto in an app, and you can follow people's, again, wearable data, clinical data, your own data, I should say, microbiome. We have a way to actually display it with others. You can follow whatever time resolution you want, daily, weekly, monthly, what have you, and be able to better see what's going on. And then we think this is powerful. This is what we're building now, personalized measurements for following people. We're very interested in certain diseases like chronic fatigue and some others. We have studies running to do this, to try and follow people's personal measurements, to be able to correlate, good days and bad days in the case of chronic fatigue, and see if we can make predictions to try and better manage people's health and productivity. This is just for me, this is showing following my time. There were 2 times I had very aberrant signals. One is when I had a bike accident, another when I got a fever. And you can pick these up with smartwatch. Now, you don't need a smartwatch to tell you when you have a bike accident or a fever. So, well, actually, it is useful for the fever because you can tell it in advance. But nonetheless, this is a proof of principle that shows this does work. So we think the wearables and this early detection is going to be very, very powerful. You can share this kind of information with your physician and do a lot more remote monitoring. We think clinical data, in a paper we had recently, wearable data is actually more powerful than what you'll measure in a doctor's office for a variety of reasons. And so we think wearables should be incorporated into medical care. And so this is what I call Mike Snyder's future. It's not everyone's. I'm a believer people will be getting their genome sequenced before birth. And together with these deep molecular measurements and wearables, we'll be able to better predict risk, catch disease earlier, and monitor and treat disease. And so that's the future that we're trying to head things towards. So I mentioned, I'll show you the wearables one in just a minute. So they'd love to have you sign up. Here's another one that's kind of interesting that can be run remotely, which is we're trying to see we have a lot of diet studies running, and we're in the middle of them. But we're trying to understand the relationship between diet and cognitive function, especially with the role of fiber, as you see here. And so if you're interested in this kind of study, I guess it's recorded. Maybe there's a way to post this on a website, or just write to me. I'd love to have you join our study. Again, you can do it all remotely. We do a little bit of these remote samplings with these small devices, and can try and follow a little bit of biochemistry, and you have to do diet logs and that sort of stuff. So here are the folks who, I guess we're in good shape, who have done the work. I won't have time to go through all of them, but I have an amazing team of people, great collaboration with George Weinstock and Tracy McLaughlin. And then on the wearables team, we have a very large team that's been pushing on us very, very hard to try to get this out to be influential, we hope, on the pandemic. And so here is where you can find the wearable study, innovations.stanford.edu. Might just leave that up for a second. So if you want to write that down, or again, you can simply write to me, or maybe I should put it in the chat. If you put /wearables, you can get to it. I'll put it in the chat. So anyway, that's the story. And I guess we'll see what questions are here in the chat. So
Thank you so much. We really, really, really appreciate it. Thanks a lot for your time. You have a lot of questions. I'm not exactly sure how much time you brought, but can you go a little over, or do you have to cut right at the hour?
No, I can go over. That'd be fine. Sure. Yeah, I probably went a little longer as planning anyway. So.
Okay, good. Then let's see how fast we can make it through. Carl, your question got uploaded the most, so you start.
So great work. Great that you got to come to our little more interactive forum here, because I've been wanting to ask you questions for a while. I heard your interview with Rhonda Patrick, and of course you just spoke at the conference, LEAF conference this weekend. But this is a great to be a little more interactive.
Sure.
So I think you'll find that a lot of us here love the work and have the same intuitions about collecting all this data and doing great science on it. And it's great that you've been gone so far already. So the high level question I want to ask is about scaling that. So let's specifically, how can the field get funding to support just a much larger cohort than 100-ish people, and ideally multi-homing it across multiple institutions? And ideally, how can we make it so that the data collection and the analysis are not necessarily forced to be tied together, but there should be some amount of money coming from funders funding this, and all it going into this sort of open data repository where all the researchers anywhere can go and do the analysis. And then and then the sort of somewhat separable sub question is, how can we incorporate citizen science so that we can, at least add some number, some higher end number of people whose data sets are not necessarily complete with every single test, but somehow that adds some value.
Yeah, I mean, you packed a lot in there. So the answer is, I would love to do it. It actually is hard to get money for this sort of thing because people tend to study illness, not health. And so we've struggled to get money. This got tucked in the way we got funding, kind of slapped it together as I normally do. Got a lot of philanthropy. That helped a lot, actually, and still count on that a lot. We did get one NIH grant when I packaged it under a pre-diabetes kind of package, and that seemed to help. But I think, and we just put in a grant. I think there is getting to be more awareness about, wellness and health. And I'm hopeful that that'll have it out. There's a lot of sort of mini national projects sticking out. There's one in Sweden and things. Not as many make their data open, unfortunately. Ours is a little unique that way, where people agreed to make their data 100% open. So I guess a few comments there. One is, obviously we'll keep plugging and try to convince the NIH to give us more money. But the other is some of the simple things like the Wearables project I mentioned. That one's easy, and we're going to put the data public. It's anonymized. We're actually the only group, believe it or not, that makes wearable data public, even though you'll read these papers. The same with CGM, as far as I can tell, CGM and smartwatch data, no one else makes their data available. Even if their paper says we're happy to make it available, you write to them, and for the life of me, I can't get it. So we are committed to that. Amazon basically gave us 1.3 million in credits to build we're calling it a data ocean, to put a lot of these data out there. So one way to do it is to bring it in that way. I'm not as sure how to aggregate it just de novo, although we sort of do anyway, right? If you sign up for a wearable study, you bring your own device and we'll download your data. So that is a great way. We have some of these other projects, especially where we start doing microsampling, where we'll do a limited amount of omics information. That data will get out there as well. We love people who make their data 100% open, including their genome sequence, for all the reasons you just alluded to, Carl. We'd love to see people share their data and let other people use it. And to be honest, as many people have run studies analyzing our data as we have, more have actually. So the data we have that I described already, it's all out there. A lot of people are using it and diving in. So, but I'd love to see more of this. And there are, the 100K UK project is a database this way. There's a new one that all of us program, but that'll be yearly sampling, and it still remains to be seen what they're going to analyze and what they'll make. You'll still have to get behind firewalls to get the data, I'm sure. But anyway, so those are some of my thoughts there. I don't know if I covered everything.
That's great. Thanks so much. I'm glad to hear a bunch of those things. And I love the fact that, I think the conflicts are not problematic. I think it's great that you're pursuing commercializing various aspects of things. Just very specifically on the QBio, like that would scale a lot if they would offer a package that didn't include the full body MRI, but was $1,000 cheaper, for example. Any plans to nudge them in that direction?
Just where they are, it's just part of, they're a new company, so they can't offer too many specialized packages. I think they have done, I should probably watch what I say, for a cheaper, well, without the MRI. No, they probably want the MRI because,
for example, some people might want to substitute the new Grail test for the MRI.
Well, as you might imagine, we're following that both academically and commercially. So hugely important. I agree. By the way, I don't think they're going to replace each other, the MRI and the Grail stuff. I think it's going to be one of those things where together they're going to be more powerful. It'll be my prediction, just based on some of the things we've done already that I talked about. So you're raising great points. You probably better move into other questions. I will stay a little bit.
Yeah, there are lots more. Joe,
Do you
it's
want to
like
read them off there,
your,
Allison? What's easiest
yeah.
to go through these?
Well, I think people sometimes want to provide some context for them. So Joe, if your question's still relevant, go for it.
Okay.
Hey there. I'm in Europe, so sorry if my internet is a little flaky. I just I love all this data, and I'm imagining a lot of people wanting to like be able to participate in stuff like this, and it just seems like a lot of work to do it in many different pieces like that. You know, there's genomes, there's MRIs, there's blood tests, there's CGMs, all this kind of stuff, and it would just be so great if there were like a single entity or company sewing it all together. Maybe it's just not how they're promoting themselves, but I looked at the Q.bio website and it seems like they're just like MRI is like, that's all they're thinking. Maybe a bunch of molecular markers and so on as well. Or do we have to go to some integrated service? Like, I don't know, does HLI do anything good anymore? Are they even around? Or is there like some fancy doctors?
Yeah, you're hitting good points. I think it's partly because we're at the early days. Now, ChIP-bio, when they launched, they wanted to stay around actionable information because it's hard to give this, like people want to share it with a doctor. So you may recall there's a company called Wearable that came out that would build these networks and things. And that was, from a research standpoint, pretty cool. But really, the information wasn't actionable, right? It was fun to see these networks, and they didn't survive. So we've been pretty cognizant of the companies I've been involved in that they have to have a proper business model. They can't just be fun. So what we do in the lab is very academic. We build networks. We do all kinds of cool stuff. We try and figure out what data are going to be useful. And then I anticipate some fraction of that's what spins off into the commercial sector.
You opened your talk with these descriptions of, here's the stuff we looked at and look at the things we diagnosed. We found this, these 3 different types of early cancers and these heart disease issues and, various kinds of precision diabetes. And a lot of that stuff seems actionable, but maybe just not like en masse in a way that you can actually make money off of it as a startup or.
Yeah, well, again, a lot of what I presented does spin into ChIP-bio or January because it's a little more focused on the metabolic January AI on that side of things. And, it's only a matter of time till I would imagine ChIP-bio pulls in January data, right, to pull in the CGM. So, and they're very keenly interested in wearables, but it's being done in a pretty deliberate fashion, as you might imagine. So give it time; it'll get there. But you're probably just as impatient as I am, Joe. So But anyway, we are trying to get there. Fair enough.
Thank you, Joe. Okay, next one up we have Brad. Brad English, that's you. In case you hear.
Hi, Dr. Snyder. Thanks a lot. Sorry, can you hear me? Sorry.
Yeah, fire away, Brad.
I was wondering if any of these very expensive, invasive biometrics that are best done in 109 people or if the work has already been done to cross-correlate this with much more non-invasive, cheaper biometrics that we could maybe think far more scalably with.
Yeah, I mean, we're very interested in that. That's where comparing the wearable data we're getting, for example, with the clinical measurements to see what we can extract from a smartwatch is one example of that. So, and then we're doing a lot. I mean, this is still, I don't know if you call it invasive, but we're doing a lot with microsampling and pricking and doing deep measurements there. So that is minimally invasive, shall we say. So we're trying to get in that direction and see what we can learn. And I'm very intrigued by the smartwatch, as you can tell, because it's dirt cheap, these data. I mean, these are $100 watches. We're doing early detection of infectious disease. And I honestly think you could put a smartwatch on everyone on the planet. 60% of the planet you probably know has a smartphone. So if you just pair that with a smartwatch, even the rural parts of the world, people have smartphones. And I think we could really improve people's health a long ways by doing this stuff. Anecdotally, people have come up to me and said, I actually heard you talk and I got a smartwatch, and sure enough, I learned that, I saw my heart rate go off and it turns out I had an infection. I had no idea, and this kind of stuff. So anecdotally, it is spreading, and my goal is to put it on everyone on the planet. And that one's really cheap.
Yeah, that's fantastic, and thank you so much for doing that. It's really inspiring. Lastly, you mentioned epigenetic methylomes for the 109 people. Is that data, as well as the battery of tests that you've done, openly published and available for sort of analyzing and getting our hands dirty with and stuff?
Yeah, well, yes and no. So we did it on me as a pilot, like 4 years a day, most expensive experiment I ever did. We did whole genome bisulfite sequencing, which is the whole methylome. And we did it because, again, we always pilot things on me to see what we can learn, because you don't know what you're going to learn. And also sometimes we screw up, and then we get it right the next time. And these samples are very, very precious. So we've been waiting for the price to drop enough to do the whole 109. We have like 2,000 samples now, 1,500 to 2,000. So we want to do it on all, but we want to wait for the price to drop. So you can get my data. It's available. It's out there. Feel free to play with it. The other 109, all I can say is stay tuned. I keep thinking we're going to do it in 2021, but now I'm guessing 2022 might be a little more likely. So maybe you can ping me back then and see what we can get you.
I was just about to say, I or someone else might ping in the future. Thanks for the great work, Michael. Really.
Oh, sure.
If none of the others will, I sure will. Lynn, we have you next.
Hi, that was just beautiful. Thank you. Having done both exercise and had viral HR spikes, heart rate spikes, how does the algorithm tell the difference between, say, I'm going for a healthy run or I've got a viral infection? And definitely post-COVID, a lot of people are suffering from postural orthostatic tachycardia syndrome. Can you be using your algorithms to pick up cases of long COVID that doctors are generally dismissing?
Yeah, so with regards to the first one, we mostly look at resting heart rate now. So when you're running, we would not count that, right? We would only look, we subtract 10 minutes after your run, which is, I do think that—
Sorry, but does that mean that people are definitely recording their runs? So say if I'm late for a bus and I run across the road to catch a bus, or I run upstairs, I'm going to have a very brief spike that wouldn't be—
Yeah, but we'll see that. We'll see yours. Yeah, but we'll see your steps, right? That'll be in your—
okay.
Because we get your step information, so we're tracking all that, and so that would be some— yeah.
Okay, of course. Yeah, sorry, I forgot
right.
It's holistic, isn't it?
Yeah, but I honestly think that walking is probably a better measurement, but we're not tuned right for that, because I think you actually see it's like a little bit of a stress. And when you're ill, it gives a bigger signal. It's like a stress echo for a heart. So I actually want to tune the algorithms to be able and use machine learning actually to pull the stuff out. But anyway, so in the future, that's where I hope that we'll go. And then the second part of your question, sorry, remind me what it was again.
It's about long COVID, people with long COVID.
Oh yeah, we definitely,
and stuff like that. Yeah.
So we're looking at those data now. There's no question. We see people who have COVID often will have, alerts and other signals going off for the next several months. And so we're going through those data now and trying to put it together with the kinds of symptoms you were describing. And we're in the middle of that analysis. I don't have a complete story yet, but we definitely detect, post-COVID signals, if you want to call them post-COVID. And I forgot to mention, you probably know that there's a nice paper from United Health Group that shows for Optum, where something like 4% of people get type 2 diabetes after viral infection. So that's a classic post-COVID thing. Fits very nicely with the original viral study we put out there. Now it goes back 2012. So I do think this stuff is very generalizable.
Great, thank you. Next one up, we have Tom.
Yeah, my question really has to do with the role of payers, that is Medicare, self-employed employer groups, insurance plans, organizations like Kaiser that both deliver care and pay for it. And some VCs I've talked to are reluctant to invest in prevention-oriented startups if the payback is longer than 18 months. And the reason is that some of the health plans they talk to are reluctant to invest in prevention-oriented interventions because of the level of patient churn that they have. So is that something that you've come across, and how do we get more both entrepreneurs and investors and payers interested in supporting prevention? Because 18 months is ridiculous as a payback period.
Yeah, that's right. And the reason for that, so this is one of the ways in which our healthcare system is broken. We don't pay to keep people healthy. We only pay once they get ill. And it bugs the heck out of me that system's set up this way. It's really backwards. So how do we solve the problem? Well, I guess the way investors are doing it now, to be honest, like QBio, it's a concierge service, if you will. We want to get it out broader. We hope to get it cheaper, starting out expensive. There's a lot of R&D costs, but as we get this scaled in ways and with some new technologies, I hope we can get it inexpensive and out to the world, to be honest. So that'll be the goal. So if it's cheap enough, I hope they'll take it on. In the meantime, I think if we can make some of these, at least some parts of this, like the wearable data, show that that stuff's so inexpensive that we could bring it in, that everybody should be doing this. And if these plans could have that I think that would help. They tend to roll it in a different way, though. Like the groups that we've talked to now, several have approached us about, well, let's take at-risk populations. Like, let's do monitoring on people who are outpatients from, some surgery or something like that, and show that it works for those folks first. So start with the at-risk group, start with, concierge, people who pay, and then show it has utility, and then try and get it broader. I think that's how it's going to roll out, unfortunately. And that's just because based on the realities of our current, the whole financial way things work.
Thank you. Lovely. Next we have Vadim and then Luke, and then we're done. Then you will be released.
Okay, no worries.
Yeah, this is amazing work. You reported or presented several examples of reversals in various measurements, for example, in response to lifestyle changes. I wonder whether this applies to aging. For example, in the case of Ageotypes or maybe wearables, basically maybe other examples of aging, whether you can see basically going up and down.
This is a great question, something we're extremely interested in. So we now have about, like I say, 7 or 8 years of data, and we're just going through the analysis now. And we have the lipid data all done, and that's turning out interesting, but I didn't quite have it far enough to present here. So maybe next time we'll present that. But once we get more data, we're going to have, I don't know if all 109, but we should have enough measurements from the bulk of those folks to be able to look in a lot more detail. And a lot of them will have undergone lifestyle changes. Like some people switch to vegan diets and things like that. And we're going to see how their profiles shift and see if any of their Ageotypes shift. So to me, I'm very excited about that, because I think you hit the nail on the head. If it's got to turn into actionable information, if we can see how lifestyle shifts lead to improvements in people's, or I guess maybe things may go the wrong direction, but either way, we want to see this and be able to, relay information back to folks. This is things that are good for you, and this quantify it, right? If you do this, if you walk, 10,000 steps a day, how much does that change the slope in certain Ageotypes? That would be pretty cool, right? That's what we want to do. So great question, Vadim. And I hope to be it'll take us a year to get to that point realistically, because there's a ton of data we got to go through.
Thank you. And your final one, Luke.
Hi, Michael. I have for the wearables question, a refinement of Tom's question, which is that we actually have funded companies that do self-insured employment. And so there are two economic benefits there. There is the cost savings that drops to the bottom line if you make your employees healthier. And then, of course, you benefit however long you have the employee. Maybe it's 18 months, and maybe it's longer, who knows. But you also have the productivity increase that also drops to the bottom line. So are there health interventions that, and this is particular to this type of insurance, this employer self-insured plans, are there particular health interventions that have productivity improvements that you think employers like this should be pursuing if they have those types of plans?
Yeah, again, 100% conflict, but the no-brainers here would be January AI and QBio. Why do I say that? January AI is trying to control people's spikes in diabetes. And I don't know about you, but I can put myself to sleep with a slice of pizza. So I know exactly what foods are going to do what to my
I've
behavior.
completely quit sugar. Like, so.
Yeah, so you might just say everybody quit sugar, but you'd be amazed how you're eating things you think you've quit, but you may not have quit. You probably have, by the way. But I was talking to a New York Times reporter. He said, "Yeah, I put these CGMs on. They're really eye-opening." And because my example is I ate a pulled pork sandwich and my sugar just went through the roof, like 350 mgs per deciliter. And I showed that to somebody and said, "Mike, of course, everybody knows pulled pork has sugar in it." Well, I didn't know. There's a lot of stuff like that. And I was talking to this New York Times reporter who said, "I thought I was eating healthy. Every day at lunch, I was having salmon on salad." Yeah, then I put a CGM on. I saw my sugar spike through the roof. And guess what it was? It was the balsam vinegar he put on top, which has sugar on it.
It's sugar. It's sugar. Yep.
It's sugar. And again, a lot of the stuff is so obvious in hindsight, right? You just hit yourself on the head. And so of course, what did he do? He just left off the balsam vinegar and everything's fine. So little things like that can make a big difference, I think. And so this is what we need. And so just putting these things on for short periods, like I say, they're very eye-opening. And so I would argue both these things have power. So I mentioned January, and there are other companies that are very interested in the space too. I think the wearable stuff will be really quite powerful. And so that would be the goal. And we are trying to get, maybe we should talk to you further, Luke, for some of these companies trying to penetrate with some of the big companies who seem interested in exactly what you were saying.
Yep. Yeah, we could follow
Lovely.
up.
Happy to do that,
Okay, let me know if I should help coordinate. Okay, I was lying. One
Please.
final last question from me, which is, what can this group possibly do to help you further your work?
Well, sign up for as many studies if you want. If you're in the Bay Area, you want to join our fiber study, we'd love that. If you're anywhere, you can join our fiber and cognition study. You should all be wearing smartwatches. If you're the quantified self group, I think you are. You probably already are. Yeah, I forgot to say I'm wearing 4 of these things. And I wear 8 of these devices every day, by the way. So yeah, by all means, sign up. Even the CGM study, we have a remote version of that. So all kinds of studies out there. So why don't you visit our website or write to me and I'll steer you. And again, if you're local, you're probably available for more of these deep profiling studies. And if you're remote, we'll still do some level of profiling, but different. We do love people who make their data completely open because I think that makes it more powerful to the world. So anyway, great.
Wow. Okay. Well, lots of, I think you'll be swamped with requests. Thank you so much for staying on. We almost made it to stay under, under the 15-minute past mark. So I'll close the poll now. I will probably follow up with you again for an update on this. It seems like there's a lot happening and you're just getting started. Thank you so much from all of us for joining, and I'll be in contact with the recording and the seminar summary. Okay, everyone, it was nice to see you. We have our next meeting on Thursday, again at 11 a.m. PDT and 8 p.m. CET, and I'll be sending another reminder email about that very shortly. Okay, thank you, Michael.
Thank you all. Bye. Great questions.